When dealing with transformer secondary protection, remember that the overcurrent protective device should be rated no higher than the secondary conductor's ampacity and must not exceed the transformer's nameplate rating. You are correct to assume that the wiring to each machine must be sized according to the machine's ampacity, not the transformer's overall capacity. If a machine has an internal overcurrent protective device rated at 20 amps, the wire feeding the machine can be sized for 20 amps, assuming it's installed according to the National Electrical Code, specifically Table 310.16. The overcurrent protective device on the transformer secondary side shouldn't be rated higher than the ampacity of the wire supplying the machine, which in this situation would be 20 amps. See National Electrical Code Section 450.3. The secondary overload device's rating must not exceed the value specified on the transformer's nameplate. In simpler terms, let's break down how to apply these rules practically. Firstly, determine the load requirements for each machine. Each machine draws 20 amps. Secondly, consult National Electrical Code Table 310.16 or the relevant ampacity table in your local code to select the appropriate wire gauge for 20 amp load, considering the wire's insulation type and the installation conditions like ambient temperature and whether the wires are bundled together. Thirdly, ensure the wire you choose has an ampacity of at least 20 amps after any necessary dirting for temperature or bundling. Fourthly, the wire should be connected to a 20 amp overcurrent protective device, such as a circuit breaker or fuse, at the transformer's secondary side. Fifthly, this 20 amp overcurrent protection protects the wire feeding the machine, preventing it from being overloaded. Sixthly, the transformer itself also requires overcurrent protection. National Electrical Code Section 450.3 dictates how to protect transformers. For transformers with a primary voltage of 600 volts or less and a primary current of more than 9 amps, the overcurrent protection must be set at no more than 125% of the transformer's rated primary current if you're using a circuit breaker, or no more than 125% if you are using fuses. For transformers with a primary current of less than 9 amps, the overcurrent protection can be set at up to 167% of the transformer's rated primary current if you are using a circuit breaker, or up to 300% if you are using fuses. For the secondary side, the overcurrent protection must not exceed 125% of the transformer's rated secondary current. Seventhly, let's calculate the primary and secondary currents for your 30 kVA transformer with a 480 volt primary and 240 volt secondary. The primary current is calculated by dividing the transformer's kVA rating by the primary voltage and then multiplying by 1000 to convert kVA to volt amps. So, 30 kVA divided by 480 volts equals 62.5 amps. The primary current is approximately 62.5 amps. The secondary current is calculated similarly. 30 kVA divided by 240 volts equals 125 amps. The secondary current is approximately 125 amps. Eighthly, considering these currents, the primary overcurrent protection shouldn't exceed 125% of 62.5 amps. 125% of 62.5 amps is about 78.125 amps. You would select the next standard breaker or fuse size up to, but not exceeding, this value. A standard 80 amp breaker or fuse would likely be used. Ninthly, the secondary overcurrent protection shouldn't exceed 125% of 125 amps. 125% of 125 amps is 156.25 amps. However, the code also stipulates that the overcurrent protection must not exceed the transformer's nameplate rating if there is one on the transformer, which in this case is 72 amps. And so, you would provide overcurrent protection at the secondary side at the 72 amps, as indicated in the transformer, or use a smaller overcurrent protection if needed. Tenthly, remember that the internal fuses and disconnects in each machine provide protection for the machine's internal components and wiring, but they do not protect the feeder wires running from the transformer to the machine. The overcurrent protection at the transformer secondary is specifically for protecting these feeder wires. 11thly, the smaller gauge wire provided by the equipment manufacturer is designed to handle the machine's internal current requirements. It's protected by the machine's internal fuses. You can use the smaller wire, but you must provide the appropriate overcurrent protection at the transformer secondary to protect the larger feeder wires that supply power to the machine. Now, let's consider a few additional points for clarity. Firstly, the term ampacity refers to the current carrying capacity of a conductor in amps. It's determined by factors such as the wire gauge, insulation type, ambient temperature, and installation method. Secondly, Table 310.16 in the National Electrical Code is a commonly used reference for determining wire ampacity. However, always refer to the latest edition of the National Electrical Code or your local electrical code for the most accurate and up-to-date information. Thirdly, dating factors may apply to the ampacity of conductors in certain situations. For example, if multiple current-carrying conductors are bundled together in a conduit, the ampacity of each conductor must be derated to prevent overheating. Fourthly, ambient temperature also affects ampacity. If the ambient temperature is higher than the temperature rating of the conductor's insulation, the ampacity must be derated. Fifthly, overcurrent protection devices such as circuit breakers and fuses are designed to protect conductors and equipment from overloads and short circuits. They interrupt the flow of current when it exceeds a predetermined level. Sixthly, circuit breakers are resettable, while fuses must be replaced after they blow. Seventhly, selecting the correct overcurrent protection device is crucial for safety and proper operation. The device should be rated to interrupt the maximum available fault current at the point of installation. Eighthly, it's important to understand the difference between overload protection and short-circuit protection. Overload protection protects against excessive current flow that can cause overheating, while short-circuit protection protects against high-magnitude currents that can cause immediate damage. Ninthly, the National Electrical Code provides detailed requirements for overcurrent protection in Article 240. Always consult this article for specific guidance. Tenthly, when working with electrical systems, always follow safe work practices. To energize circuits before working on them and use appropriate personal protective equipment. 11thly, it is always best to consult with a qualified electrician or electrical engineer to ensure that your electrical system is safe and compliant with all applicable codes and standards. To summarize the key points, firstly, size the wire to each machine based on the machine's ampacity, not the transformer's overall capacity. Secondly, protect the feeder wires with an overcurrent protective device at the transformer secondary, sized according to the wire's ampacity. Thirdly, protect the transformer itself with overcurrent protection on both the primary and secondary sides following National Electrical Code Section 450.3. Fourthly, use the machine's internal fuses to protect the machine's internal wiring and components. Fifthly, always consult the National Electrical Code and local electrical codes for the most up-to-date requirements. Sixthly, if you're unsure about any aspect of electrical system design or installation, consult a qualified electrician or electrical engineer. Seventhly, remember that safety is paramount when working with electricity. Always follow safe work practices and use appropriate personal protective equipment. Eighthly, this information is for educational purposes only and should not be considered a substitute for professional advice. Ninthly, electrical codes and standards vary depending on your location, so always check with your local authorities for specific requirements. Tenthly, proper grounding and bonding are essential for electrical safety. Ensure that all electrical equipment is properly grounded and bonded according to code requirements. 11thly, regular inspections and maintenance are important for ensuring the continued safe and reliable operation of your electrical system. The National Electrical Code is a comprehensive set of standards for electrical installations. It's published by the National Fire Protection Association and updated every 3 years. Familiarizing yourself with the National Electrical Code is essential for anyone working with electrical systems. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It's important to understand the relevant sections of the National Electrical Code for your specific application. In addition to the National Electrical Code, there may be local electrical codes and regulations that you must comply with. Check with your local authorities for specific requirements. Proper electrical system design and installation are critical for ensuring safety, reliability, and compliance with applicable codes and standards. Always follow best practices and consult with qualified professionals when necessary. Remember that electricity can be dangerous, so always exercise caution and follow safe work practices.